Okay, so I'm going to hit this second objective, probably the third one too, hopefully in this video. Then I'll try and maybe there's already a video I found, I think it's an online video for volt drop, but maybe then next week I can do the volt drop too. But I'll get through these next two objectives here. They're not too bad. Neutral conductors especially, it's not terrible, but sheath currents has a few little tricky things in it, but so to start off, we're going to do these neutral conductors. So we talked about this in second year. The only time I talked about it in second year was in apartments where we had very large feeders going to an apartment over 200 amps easily. And we would have a potential where we could reduce the size of the neutral based on the fact that the expected return on it wouldn't be as large. So in the field, I didn't do that ever, but I mean, I could see if you had a large supply or large service coming in, that could save a decent amount of money if you could reduce the size of your neutral conductor. So definitely possible. So we'll go through the scenario here. So first thing they talk about are from Rule 4-018. So we'll get that out here so we can make sure that's what we're referencing. Okay, so right at the very bottom, and then on to the next page. So the neutral conductor shall have sufficient ampacity to carry the unbalanced load. So we've talked about that in three-phase, and even in a Edison three-wire scenario, the neutral is going to carry that unbalanced current, so it has to be sized appropriately for that. So I'll read through these rules, and then we'll kind of hit the module and show exactly what they say too. So the maximum unbalanced load shall be the maximum connected load between the neutral and any one ungrounded conductor as determined by section 8, but subject to the following. Okay, so the maximum unbalanced load shall be the maximum connected load between the neutral and basically one ungrounded conductor. So just to kind of reference, that's what they're talking about first off in the module here. So here's my Edison 3-wire. If these are balanced, these two lines or ungrounded conductors are equal, I'll have 0 amps traveling back on the neutral. And then in this scenario, they say we got a fuse blown now. Well, now I have 0 on this ungrounded conductor and 300, so the difference is what's going to come back on the neutral. So now I got 300 amps coming back on this neutral. So that's why we got to make sure that it's sized appropriately for that. Okay, so that's what the first part is saying, but then it says subject to the following. There shall be no reduction in size of the neutral for the portion of the load that consists of electric discharge lighting or nonlinear loads. Okay, so that's like computers and such. And it says B, except as required by otherwise by item A, so these two loads we can't derate, a demand factor of 70% shall be permitted to be applied to the portion of the unbalanced load in excess of 200 amps. So if I don't have electric discharge or nonlinear loads and I'm over 200 amps, anything that's over 200 we can reduce to 70% is what that's saying. Okay, the size of a surface neutral shall not be smaller than the size of a neutral selected in accordance with sub rule 1 and shall, so sub rule 1 is the rule prior, and shall not be smaller than number 10 copper, number 8 aluminum. Okay, just so keep reading through those, but the module is going to go through here and explain the scenarios they're talking about. So again, first off, we want to make sure we have an understanding what happens when we lose the line. We do get that full current going back. The difference between the two ungrounded circuit conductors is going to come back on that neutral. So again, here, this is where it talks about now anything above 200 amps, we can apply 70% to. This is where they're talking about we cannot apply the 70% if they are discharge lining or nonlinear loads. So we got to take those out if we want to derate anything above that 200, but it includes those loads. And they explain why here is the harmonic currents can add a neutral current to a point where if we derate those, our wire might not be big enough because we do get extra current flowing through because of those harmonics. So here in this example, we have an unbalanced load on a 122.8 panel. It's got 370 amps. Electric discharge lighting counts for 75 amps. And there's 20 amps of computers. Okay, so that's those two loads that we can't derate. So the solution, there can be no reduction in the neutral conductor for that portion of the unbalanced load consisting of electric discharge lighting or nonlinear loads. The total load may be considered in determining the reduction in the neutral current size. Okay, so what we're going to do is We're going to take away the discharge lighting and the nonlinear loads, get them out of the scenario first because we can't derate those. So we do that, we're left with 275. Well, the rule said that anything above 200, we can derate down to 70%. So we take that 275, subtract 200, what's left is 75, and we can derate that portion. So we get 52.5 amps of the 75 that we were allowed to derate. Now, the big thing is we got to make sure to add everything back that we took out. So first thing we did is we took out the 200 that we're not allowed to derate at all. We took out the electric discharge lighting and the nonlinear loads. So we have to add those back in here, and then here's the reduction of the 75 down to 52.5. So selected neutral is 500 kc mils, RW90 with a default conductor temperature termination of 75 degrees. Okay, because it's above 100 amps. So the big thing for that is making sure we add these back in. Okay, that's probably the biggest mistake that people make is they take these out, then they just add 200 and this together, and they forgot to add these back in. So just watch that. So basically what's happened now is we went from 370 down to 347, and they can definitely get us into a different wire size. Okay, so by using this rule, we can change the wire size and potentially save some money if we're doing a larger install or multiple installs of the same type. The objective 2 exercises, all right, we'll just kind of go through these here just so you guys have an idea. Again, if you want to try these on your own before you listen to me explain it, by all means. Figure 6, what's the maximum unbalanced? Well, the maximum unbalanced is going to be if any one of these fuses blows, what's the maximum current that's going to flow? I'm just looking at 63 and 60. Obviously, 63 is the larger of the two, so that would be the maximum unbalanced load that could go back on the neutral. Okay, the next question, what size of aluminum? Okay, so you see I circled that because that's depending on what table we're going to go to at the end. Conductor is required for the neutral of a feeder in a conduit that supplies a 3-phase 4-wire panel board with a maximum unbalanced load of 438 amps. Electric discharge lighting is 38 amps and 40 amps of computer. Okay, so just like the example prior, I get my total amps, I subtract the 38 amps of discharge lighting, the 40 amps of computer equipment because we can't derate these. Okay, so we take them out, we're left with 360 amps. Then we take the 200 out that we aren't allowed to derate because we can't derate it till we're above 200. So here's the 200 that we have to take out. And then I'm allowed to derate 160 because that's 200 minus 360. So I take that at 0.7, I add it to the 200, and I got 312. Now again, the last step, don't forget to add in these guys back after the fact. Again, we can't derate them, but it doesn't mean we just get rid of them. So we take our derated value now, we add in the discharge lighting and the computer, and then we get our total current. Okay, and then we can go to our appropriate table and find our size. Again, if they don't give you a temperature termination, use your defaults. That's how you're going to find that. Okay, so from 4-006, if I'm not mistaken. Okay, so we went from having 438 amps originally, and now we're down to 390. Again, potentially a wire size and saving money. Okay, so that's the neutral reduction. Next objective, they talk about sheath currents. Okay, so they say the big issue with it is when we have single conductors, we have these magnetic fields that are being developed around these conductors that are constantly expanding and contracting. So I always look at it like I have a field around a conductor, it's at 0, and when I'm going through my sine wave, it's peaking, so it's large, and then it's going back down to 0, so it's getting back to 0 again, no more magnetic field. Peaks again, maximum magnetic field. So it's doing that at the same frequency as the supply. So there's motion there. What that does is that induces a voltage into a sheath if it's surrounding that conductor. Now what they're saying here is multi-cable conductors, it's not really an issue because they have current going back and forth on different cables and they'll actually cancel each other out, the magnetic fields. Okay, so it's not such a concern with the multi-conductor cables, it's more with the single conductors. Okay, so they do kind of show a picture here of the magnetic field developing around that conductor. So again, AC, so alternating, that means the magnetic field is constantly expanding and contracting, every time we go through our sine wave. So again, at 60 hertz. And we want to basically make it so that there isn't a path to flow, to make so that these sheath currents can flow on that sheath. If we ground it at both ends, we've completed the circuit. So we do have currents flowing through there. And again, so much so that we could get damage to the insulation, okay? Because current flowing obviously creates heat and then damages the insulation, okay? So we want to make sure that we can eliminate those, or we have to limit the amount of current going through the cable to make sure that it's not going to affect it. Okay, so two scenarios. We either got to eliminate or we have to derate. And eliminating, it seems to be, would be the easiest, or the, maybe not the easiest, the best scenario. And it talks about in the appendix how we're going to do that. So I'll talk about this little chart they have here that they made up in the mod, which is kind of nice. Obviously, I have an understanding, as you will, that this is not available for you on your test. So all this information, I'll flip here in a sec, is from Rule 4-001C and Appendix B. Okay, so I got that's page 592 in the code book. That's where we're going to find out about where this information they're talking about here. It's mainly from that appendix there. Okay, so but let's just go through this quick, and then I'll go to the appendix and show you where it says this stuff. So does it involve single conductor cables? Yes. Are we going to derate or eliminate? If we can eliminate them, then we just basically don't have to derate, and we eliminate them based on Appendix B. Okay, and we'll go and check that out. If we're going to derate, is the installation free air, raceway, or underground? Okay, that's the three scenarios we're going to look at. So if it's underground, the ampacity depends on the cable arrangement. So that's from our diagrams D8 to D11, those underground tables that we have with all the different details. If it is underground, then we're going to reduce, and sheath currents have not been eliminated, we're going to reduce the ampacity to 70% of the values in the tables. So basically we're derating because we've decided that either in this scenario we cannot eliminate, or it's not easy, or whatever the case may be. So we do have to derate our cables in that scenario. In a raceway, if the raceway is ventilated or ladder type cable tray with proper spacing, then free air rating may be used. So then we go, if that's the case, then we just go over here to the free air. It's basically saying if my ladder cable tray is ventilated and my cables are spaced properly, it's almost like they're running free air. Okay, but if they're not, and we don't have proper spacing, or if it's another raceway or not a ventilated ladder type cable tray raceway, then we use 70% of the ampacities from tables 2 and 4. Again, those aren't free air, those are now as if they were in raceways. And we apply table 5C when necessary. So that's if we have more than 3 conductors, we have to apply deration from tables 2 and 4. Okay, so if we had 4 or 5 conductors, we'd have to go to table 5C and then also apply that as well. Okay, free air, if the load, this is an important caveat here too, if it's less than 425 and proper spacing is maintained, we use the ampacities from table 1 and 3 with no sheath current derating. So basically they're just run like free air. We go to table 1 and 3 and size our cables accordingly. Again, we use 5B or D, that's based on the spacing. Okay, so if the spacing isn't at 100%, 5B or D is going to give us some derations for that. If it's over 425 amps, the ampacity is reduced to 70% of the values. Again, this is because we haven't got rid of the sheath currents in tables 1 or 3, and then apply 5B or D again based on spacing. So the flow chart is based on rules 4-004, 006, 008, and Appendix B and D. Okay, D is the details for the underground stuff. B we'll go to here in a sec, and then these are the rules about how we can eliminate sheath currents. Okay, so in Appendix B, it's going to go through and tell you, kind of going to relate back to this stuff from the module where we're getting this 425 amps from and stuff. Okay, so this is from, again, page 592 in your code book in Appendix B in association with Rule 4-008. So big thing here is they'll tell you right here that for cables carrying currents up to and including 425, sheet loss can be reduced to tolerable levels without the need to apply derating by spacing cables approximately a diameter apart. This reduces the induced sheath voltage by virtue of the three-phase field cancellation effect at closed spacing. So for cables that are greater than 425, it's necessary to apply a derating to avoid the overheating. Okay, so that's where it's saying it right there. That's where we're getting the 425. The other thing they say here is to eliminate them. So to eliminate the flow, it's necessary to ensure that all paths through which they may circulate are open. Cable sheath should be grounded at the supply end only, and thereafter be isolated from ground from each other. Sheath isolation may be attained by installing the cables in individual ducts of insulating material, by employing cables jacketed with PVC or other insulating material, or by mounting unjacketed cables on insulated supports. Okay, so that's other ways we can basically eliminate the sheath currents so that we don't have to derate. Yes, then it talks about the external effects, on the single conductors, and then goes through on the next page, single conductors or single conductor cables in free air, and then the underground locations too. Okay, so that's where it's getting all the information. And I'll let you guys read through that, and it'll help you kind of use this again, but on the understanding that once you get better at them, you won't need this so much, but use it to get through the first little bit here until you get a better understanding. Okay, so in this example here, they kind of go through and do an example on this on an underground one. So they're saying single copper conductor aluminum sheath cables will be used to supply non-continuous 700 amp, three-phase, three-wire industrial load. Cables will be run in separate PVC conduits underground, shown in diagram D9, detail 1. The cables will have their sheaths bonded together and bonded to ground at the supply end. So, first, you must consider the following two questions. Have they been eliminated according to 4-008? So, to determine the requirements of 4-00, have they been met? The answer is yes. PVC conduit fulfills the requirements of 4008. What is the ampacity of these cables according to rule 4004, diagram D9 and table D9A? So the sheaths have been bonded together, ground at the supply end to meet the requirements of 4-008 Appendix B. Cables will not have to be derated. Okay, so we've eliminated the sheath currents in this scenario, so we don't have to apply that 70% derating. So in regards to the second question, we're going to take 700 amps. Again, this 0.866 is based off of table D9, and that's where the table's all based on 90 degrees. So we talked about this in the previous objective, but it's off these tables here. So D9, okay, where we've got our different details, but then down here it says these are for 90 degrees, and if we want to use 75, we have to derate to the 0.886. Okay, so that's why they're doing that, is because we have no temperature termination listed, so it's a 75 degree temperature termination. Okay, so that's why they're doing that number there. Then it says table D9A lists 900 kc mills having an amp capacity of 832 with a direct connection to the equipment. Default termination temperature needs to be observed, which is 75. Okay, so basically we just go to 9 then, and if we look at the detail 1, so we're going to go to the ampacity, we're looking for detail 1, and we're looking for that 790 amps after we increase it. Again, we have the load of 700 amps, so we're going to divide by the 0.866 in order to basically inflate our ampacity so that we're picking a wire larger so that when we potentially have to derate based on the fact these are for 90 degrees, not 75, that we have enough room in our wire size to do that. So we're looking for that 790 amps going down here. Again, this 750 would be too small. 750 kc mil, or the 754 amps. We're looking for 790 amps, so we have to go up to this 832 amps, and we have to use a 900 kc mil. Okay, so that's what that example is showing. These questions here, I'll kind of just go through it fairly quick, again, just to kind of give you a better explanation on the answers than what the module does. The module just kind of tells you the answer. I got a little bit of a better breakdown here, but definitely try and do these questions first, and if you can't get them, then have a look here, and this will help you out. Okay, so for the first question, we have a non-continuous 500 amp, 3-phase, 3-wire load supplied from single copper conductor aluminum sheath cables, RA90s. These cables will be installed in a ladder type cable tray with no other cables present. They will be spaced 2 cable diameters apart. Okay, remember the minimum was 1 cable diameter, so we should be good on the spacing. But sheath currents will not be eliminated. What is the minimum size RA90 copper required? Okay, so here's my explanation here for number 1 because I kind of ran out of room. So again, ladder type cable trays got me going to rule 4-004, sub rule 23, which is basically saying that we have to make, well here, let's go and have a look at it. 4-004-23. So this is where it's saying right here. In a ventilated and ladder type cable trays where airspace between adjacent insulated conductors is both maintained at greater than 100% of the diameter of the largest conductor cable, the ampacity of the conductors shall be as follows. So for single insulated conductors, single conductor cable, basically we're going to tables 1 and 3. Okay, so that's because we got our spacing good, so we don't have to worry about going to table 5D because our spacing is decent. Okay, so I have that note here. No table 5D because they're 200% apart, greater than the 100% of that rule we just read. Okay, but we do have sheath currents still, okay, because they haven't been eliminated. So that's where we take the load again of 500 amps from the question. Now we're dividing it by 0.7, again, to basically inflate the expected ampacity so that when we choose a conductor, we have enough room in the conductor to derate it to that 70% and still cover the load. Okay, so we inflate our ampacity. Then we go to table 1 because it is copper. It said to go to, this rule tells us to go to table 1 or 3. That's based on whether it's copper or aluminum. And we go to the 75-degree column because it was not listed in this question. And so we went by the default, which is because it's over 100 amps, we're using 75 degrees. And we can go and choose a 700 kc mil wire that's good for 755 amps. So we can see even in this question that potentially derating is significant. Okay, so we went from our load of 500 amps to now an inflated load of almost, at least, well, 200, more than 200 amps higher. So that's definitely more wire size. So if we can eliminate these sheath currents, we can avoid this scenario, right? So it seems like that would be the easiest thing, but again, who knows? Scenario. Question 2. A non-continuous 380 amp 3-phase 3-wire load is to be supplied from a panel board by copper single conductor Tech 90 cables run underground as per diagram D8, detail 1. Sheath currents will be eliminated. Awesome. When installed according to the manufacturer specs with special permission. So what is the minimum size that we need? Okay, so again, now we go into this solution here. We have a 380 amp load. We're at a 75-degree temperature termination, okay, because again it didn't state, so we're using the default. Then we're just going to diagram D8 detail 1 to find out what the ampacity is. So we basically need to go and find a wire for 380 amps, so we're going to go to diagram D8 detail 1. So again, just like we were talking about in the previous objective, we want to always make sure and check the pictures so that they're not parallel runs, because it says detail 1, diagram D8. And then we just want to make sure, is it copper or aluminum, because D8A is copper and B is aluminum, so we're looking for copper, so we're going to be going to D8A. And again, we have to watch because this was a 75-degree temperature termination. This table is 90 degrees. So there is that deaeration factor. So before we pick a wire here, we have to, again, inflate our load ampacity by this value in order to pick a proper conductor and have it be able to be derated. Okay, so we're going to take this 380 amps, and then we're going to divide by that 0.886, and we get this now inflated current again of 428.89 amps. That's the number we're going to go to the table with, and we look here, and we're looking for 458. Well, dang, it's right on there. So 4-aught, and that's what we're going to use is 4-aught. Okay? So don't forget about that 75-degree temperature termination, okay? Because that'll bite you for sure, and you're gonna do it right and forget that and get it wrong, okay? So last question that they have for this example is a non-continuous 450 amp three-phase three-wire load is supplied by three single conductor aluminum sheath RA90 cables in a ladder type cable tray. Spacing is maintained at greater than 100%. Okay, so we shouldn't have to use 5D of the large or the other 5A either. I can talk about those here in a sec too. I'll go back to it. Because the spacing is good, sheath currents of a value that are likely to cause temperatures greater, so they have not been eliminated. Okay, so we're kind of in the realm here of this ladder type scenario. So ladder type is the proper spacing? Yes, then we can kind of treat it as free air. So that's when the 425 amps is going to come into effect. Is it less than 425 proper spacing, or is it more over? Okay, and in this case, our load is 450. So we're definitely greater, so we have to derate. So we're going to take that 450, we're derating here with this 0.7 because it's over that 425. Okay, so that's what that kind of flow chart is showing us. We're in this scenario right here. Okay, so we have to, that's why we're having to derate it there with that 70%. So again, we want to, because we have our load ampacity and we're looking for a conductor, we want to inflate the potential load. Again, that's not what it's going to draw, the load. It's going to draw 450, but we're inflating the potential number before we go select our conductor so that we can derate without issue and still cover the load. So again, we have greater than 100% spacing, so we don't have to go to 5D. Over 24 and 25 amps, so it's 70%. So then we go to table 1 because, again, the spacing is good, so we're basically treating it like a free air installation now, and they are copper, so we're going to table 1. So then we go to table 1, and we're looking for 642.86 amps. So if I go to table 1 to find out which conductor we should use, and I'm looking for, again, our inflated value of 642, and we're under the 75-degree temperature terminations because they weren't listed. So we're going down looking for 642, and we're going to be at 690, and we're going to use 600 kc mil. Okay, so again, significant gap between the original 450 amp, which would be 350s, and now we're all the way up to 600s because we didn't eliminate those sheath currents. Okay, the other thing I want to kind of just touch on here is that table 5A, or sorry, not 5A, 5B and 5D. So 5B, and they reference this in rules 4.004. Basically, if we have spacing less than 25%, this is what we're going to use. Okay, and then if we have spacing that's not 100 but higher than 25, this is where we're going to go to 5D. Okay, and the rules that say that, in not so many words, is rule, again, we're into this large 4.004 ampacity of wires and cables. And subrule 8 here saying where the free air spacing between adjacent and single conductors is maintained at not less than 25, but not more than 100, so in between these two, we're going to use correction factors from 5D. We're up to including 4 single conductors or cables in free air space less than 25%, then we're going to go to 5B. Okay, so that's the rule that's going to bring us to those tables. So again, it's all about the spacing. So when you're doing questions, check the spacing. Check how it's run. Is it free air? Is it underground? Have sheath current been eliminated? If not, we have to potentially derate. Okay, again, based on ampacity, if we're free air, or just derating if they're underground. So go through our blackboard questions. We're definitely going to get you through a bunch of those style of questions. I'll maybe pick a couple to do here live for you guys so that we have an understanding. So work through that. I'll see about maybe doing a separate video for volt drop, and I'll post it later.